All right, finally for our last lesson in the force list, at least for my classes. If you are not in one of my classes, right now, at least as of the filming of this video, we have left spring force off from the force list for Unit 2. For a couple of reasons, I and my colleagues actually like to cover spring force when we begin Unit 3, where spring potential energy comes into play. So we just kind of move it over there and do all of the springs at once. If you are a student not in my class, or in the future if we end up changing things out, I'll probably have another video that's added to this a little bit later that will go through the introduction that you would need for spring force and solving some of those examples. So functionally, you might have one more lesson after this, but for any of my students currently watching, this will be the last one that we need to take a look at to finish up the majority of, or all of our force list. So, moving forward. The main one that we're going to take most of the time looking at is going to be tension, or force of tension. In this case, this is the force through a rope, or string, or wire, or sometimes cable. I think the AP exam is going to try and clean things up a little bit. On the front cover, at least of the latest version that I saw, they said to assume, unless otherwise stated, that all strings are ideal. In other words, you don't have to worry about them breaking, and they're lightweight, they won't cause any problems or throw anything off. So I think they're going to preferentially use strings instead of rope, wire, cable. But just to be safe, I want to introduce all of those terms as things that you might hear. Okay. So now that we've introduced that, let's see. I'm going to add a little bit more on this. The force points in direction of rope. Or string, I guess, in direction of string. It's a force that points along the rope or string. Let's see. Yeah. Here's my regular demo. Okay, going to grab that and have it ready. Okay. The abbreviation for this is capital F, subscript capital T, or sometimes just capital T, which can be a little confusing with capital T we'll see later in this unit is actually used for the period, the time it takes for one complete cycle. In some of the problems, including the example one that I have for us to take a look at, you're going to see why many of us, myself included, will actually drop the F for a capital T for tension. Most likely you'll be able to tell the difference between it and something else from context. While I badmouthed previously using a capital N for normal force, and I stand on that hill, I will die on that hill. This is a common one for you all to change to just T, and a lot of times our grading rubrics may just say that so you don't end up with a weird like cascading staircase of subscripts. You'll see it in the example and I'll point it back out to you, but I do want to point out that both of these are standard notations and regularly used. The force of tension has no equation. In fact, many teachers don't even treat it as a different force other than just by name. They'll say that a force of tension is just like a normal force. But there are a couple of distinctions that I want to point out that can be helpful and clear up some confusion on it. So I don't consider the force of tension to act exactly like a normal force, but they are very similar. Just like a normal force, you will either be given that value or you'll need to solve for it using Newton's second law, as we are going to see as we go through our example. Okay, there are a few things that I want to point out on this. First one is, a force of tension cannot push, can only pull. I'm going to show you this. Right offhand, you might go, okay, that's a small distinction. Why are we talking about an entirely different panel for that? There are some advanced applications, especially in circular motion, where it can be very useful to remember that strings can't push, they can only pull. So for instance, let's say I got object A and object B and I attach them with a string. Object A can pull on object B, applying a force through the string, a force of tension. But what it cannot do, it can't push object B. So strings can only pull, they cannot push. Okay? So that's one thing that I want to emphasize on that. That does allow you that when you see a string, you can actually predict which way the force is pointed. We know that it's pointed along the string, but if I've got a string like this, it could be going up and to the right or down and to the left. Which way is it going? Well, it depends on which object you're looking at. If I'm looking at this one, the string can only pull, so it must be pulling down to the left. If I'm looking at this one, a string can only pull, so this force must be up and to the right. This is one of those places where this can be very helpful to understand exactly which direction, which sometimes might be a little confusing. The other thing that is commonly used, and a way of thinking about it, is can change the direction of a force. Change direction of a force. At least functional. It's not actually changing the force itself, but I'm going to show you what I mean by that. Okay, so I've got a 1 kilogram mass here. So 1 kilogram times, let's assume the acceleration due to gravity is roughly 10 instead of the 9.81, so that we can do this in our head, though I guess 9.81 would have been fine, but 10. This is a 10 Newton weight that I've got here. It is being pulled down with gravity, by gravity, with 10 newtons. I am applying an upward normal force of 10 newtons, balancing out the forces and resulting in a zero acceleration. That is not a Newton's third law connection, because I could push harder and accelerate this upward. So if 10 newtons down and I push 11 up, it would accelerate upward. Or I could push less hard up. If it's got 10 newtons down and I only push up with 9 newtons, it accelerates downward, begins falling, but not just dropping it, falling, maybe a bit slower. Okay, but here's the thing. Gravity's pulling down and I'm applying a force upward to counter that out. Now, one of the things that I can do is I can hook this onto a string, and I think I can hook it onto the string. I have faith in myself eventually. Okay, now gravity, 10 down, force of gravity, 10 newtons downward, and I'm applying a force of tension upward. Now, technically it's a normal force because it's two things physically touching, but to make it easy, whenever you're dealing with a string, just treat it as a force of tension. Now, I'm not exactly applying the force of tension, I'm actually pulling on the string. I'm pulling up with 10 newtons, and the string is now carrying that force over and applying it onto the hanging object. But we've got 10 down and 10 up, so the object can remain there. Acceleration of 0, it continues doing whatever it was doing. Now, one thing that I want to emphasize on this is, here's a great example of not, just because you have a force of gravity, there does not have to be a normal force up. It all depends on what's touching the object. So that's one thing I wanted to introduce. But I am still pulling up with 10 newtons. Now, this next part where I said, with a string, you can change the direction of a force. Here's what I mean. Here's another thing that I can do. Now, I am pulling here. I'm still pulling with 10 newtons, but now I'm pulling down with 10 newtons. In order to hold this thing up, I'm actually pulling down. Or I could pull to the side, to the right, with 10 newtons. Because the string sends that force through the string. Tension is a force directed through the string, and so it follows along with the string. And as a result, at least this hand is applying a force of 10 newtons, and the string allows me to change that direction. Now, later we'll look at the forces on my other hand, and we'll find that I'm actually having to do a lot more than 10 newtons on this one, but we'll get to that when we get a chance. Okay. The key thing that I want you to understand with this is you can effectively look at it as strings being able to change the direction of a force. And when you get more comfortable with these, sometimes that can save you a lot of time and effort by knowing that. Okay, so here is the introduction on the force of tension. Let's jump into an example problem with it. We're going to look at hanging a sign. Now, what I'm going to do here is I'm going to draw two walls. We're going to say that this is a hallway. This is a great time for me to get you used to this notation. You may see this on the AP exam. Instead of it just being two lines that might be like curtains or something, a lot of times they'll put these diagonals here, and that's to let you know that this is something that's immovable. It's nice and solid. Sometimes they'll do it on flat, horizontally, and it's to represent a table. But here's what we've got. I want to hang a sign. Here's my sign. And I'm going to put a smiley face on it. What it should actually say is maybe something like bathrooms or exit or something like that. And we're hanging it here in a hallway. I want you to think of like a shopping mall. If you go to a mall, a lot of times the ceilings in those are like super duper high. And if you were to look on the side of one of the main thoroughfares, sometimes they have a little hallway that has like the bathrooms are back that way or emergency exits. And they need a sign to actually emphasize that, like the top of your head is here, but the actual ceiling may be way above it. So if they put strings just straight up to the ceiling to hang the sign, well, then it would sway in the wind and possibly be hard to read. So here's what we're going to do. We have two strings that are supporting this sign. One is horizontal. I'm going to call this string 1. And then we've got another one that has to go diagonally, string 2. And the reason why is we're going to say that where we want to hang this, maybe there's a sprinkler there, or some pipes, or a light fixture, something that according to code has to be there, and this is where we want to put the sign, and therefore we can't put the string just straight over to it, so we have to raise this up a little bit. Okay, that's me giving you a reason why we might do this, but this is a good example to finish up our force list with examples and to see all the key things that you need to see. One thing that we have not yet seen is a force at an angle. Which brings me to, I will tell you that rope 2 is actually at an angle of theta with the horizontal. Okay, so here's what we're going to do. I'm going to fill in some information. I am hanging a sign. We will say that the mass of this sign is maybe 2 kilograms. It's about 5 pounds. Okay, here's what I would like to know. Let me see. Hard to read my notes. This angle, theta, is equal to 60 degrees. We're at 60 degrees with the horizontal here. Okay, so that's what this angle is. Here's what I would like to know. I would like to know the force of tension in rope 1, and I would like to know the force of tension in rope 2. Why do I want to know that? Well, what I'm actually doing is we're designing this sign. I want to go to the hardware store and get string or wire that will be strong enough to hold the sign. In order to do that, I need to know what the forces are so that I know how big of wire I should get. Now, most students will go, just buy the biggest that they've got, man, then we don't have to do this work. But that makes for a poor engineer. What you want to do is develop these skills so that later, if you go to work in industry, a company doesn't want to just throw money at a problem and get the heaviest thing. They want you, people like you, to solve this and find, okay, what gets the job done but keeps our costs down? And if you own that company, you want people to be able to do that too. So that's a little bit of why we're doing this. I know for many students you just care about this is what's going to be on the test, so I need to learn this and do this, but I want to give you a farther view so you can understand why we're doing the things that we're doing. Okay, moving forward. You can start to see it here. We've got FT1, FT2. We're writing a bunch of little subscripts, which can get it to be a little pain. So it's common to actually just call this T1 and T2 to make it a little bit simpler. We're going to see that it's going to get even more so. Okay, I need to find these forces, and as we just introduced, there's no equation. So, just like the normal force, let's go to our free body diagram. Going down my list, we've got a force of gravity downward, the mass of the sign, times the acceleration due to gravity. And while you might be tempted to put a normal force up, here's one of the reasons that I mentioned that just a moment ago, there isn't anything holding it from the bottom. This thing is only being touched by the strings. Now, some teachers might then say, okay, well, that's a type of normal force. If you're in their class, follow whatever rules they've got. But for me, I like to keep that as a separate force. So no normal forces, nothing is touching the sign other than my strings, which I'll get in the force of tension. Since there's no normal force, and normal forces are a key part of frictional forces, as we learned last time, if your normal forces are all equal to 0, you won't have friction. In short, the sign's not trying to slide against anything because it's not even touching anything, so we got no force of friction. Okay, now we get to the interesting part. We have a force of tension. We have several forces of tension. FT1. I know that it is horizontal, but I don't know if it's to the right or left. Oh, but yes, I do, because a string can only pull, it can't push, and therefore FT1 must point to the left, FT1. Great. Then FT2. Now here's the other thing, the last key thing that we need to take a look at is a force at an angle. Now, I've colored this in purple because purple is the combination of blue, vertical, and red, horizontal. Okay, This is my force of tension. Ft2 is pointed up and to the right at 60 degrees. Once again, ropes can only pull, they cannot push. So we know that the string must be pulling it up and to the right, because that's the pulling. Okay, air resistance, we don't need to worry about that, and there are no rockets on this sign, no springs either, and therefore here's our free body diagram. Okay, the idea on the sign is we want to hang it there and have it stay there, so we'll go ahead and point this out. We want our total acceleration to be 0 meters per second squared. That will keep the sign where it's at, and that's our goal. You will not always have that the acceleration is 0. It depends on what you're trying to do in each problem. Okay, but for this one, this is what we want. Taking a look at this, I can do the following. I need to apply Newton's second law because I have all of my forces. But once again, we must apply Newton's second law in each direction independently. So I need to have my sum of forces in the x is equal to my mass times my acceleration in the x. And my sum of forces in the y must be equal to my mass times my acceleration in the y. Now, one thing that I can bring up, we want both of our accelerations to be 0. So in this case, we want all of our forces to balance out. We want our forces balanced, to have an equilibrium where we balance all of our forces. Everything's equaled out. Okay. My problem is this. I can work with the one that's in the vertical direction, gravity, and the one that's in the horizontal direction, tension 1, but tension 2 is a little weird. It's off at an angle. So what I really need is this. I'm going to draw tension 2 once again. It looks like this. Force of tension 2, and it's at 60 degrees above the horizontal. Now, as a vector, it has both an x component, ft2x. You can see now, this is why I end up calling it t2x, because this is where it starts getting a little bit silly. By the time you're writing this many, it's a pain. Over here, we've got ft2y, the y component of it. Okay, but I've now marked these out. On my exam or the AP exam, if they ask you to draw a free body diagram as part of a free response question, do not draw these components in on that free body diagram, because these are the parts of this force, not independent forces of their own. You should be drawing the total force and then looking at its components away from the free body diagram as we're seeing here. Okay, so which place do I want to start? I have two different possibilities, the x direction or the y direction. I'm going to bring up this, here's some problem solving recommendations, and once you get more used to it, maybe these will jump out at you. I know about what's happening in the y direction at least a little bit because I know the mass, 2 kilograms, and the acceleration due to gravity, but I have no idea what's happening in the x direction other than I know it needs to balance out. So I'm going to go straight to the y direction because I have more information on it. In this case, I have all of my forces in the y. Well, I've got part of ft2 in the y direction. That's ft2y, and that's positive because it's up, minus msg equals our mass times our acceleration, but that's just going to be 0. So my y component of the force of tension 2 has to balance out gravity. That's what we're saying conceptually. That's the only part of this that's y, positive y, so it must be countering out gravity to hold this thing at a 0 acceleration where it's at. And we see that here, ft2y, this part of it, is balancing out gravity. So we would have ft2y is equal to msg, but that is equal to 2 kilograms times 10 meters per second squared. Once again, we're going to use the AP simplification, and we get ft2y is therefore equal to 20 newtons. But that's not actually ft2. I wanted ft2, not just ft2y. But if this is 20, now I know one side of my triangle. I've got the opposite side, and I want the hypotenuse, so I could go with sine of 60 degrees, my angle, equals my opposite side, which we now know is 20 newtons, over my hypotenuse, which is ft2. I now do a little bit of algebra, and I can find that we get ft2 is equal to 20 newtons divided by sine of 60 degrees. And that will give me sine 60, and then 20 divided by that gives me 23.09. So I would call that probably 23.1 newtons. And this is FT2, so this is one of my answers. Okay, great. But it wasn't just one force that I'm looking for. We've got FT2, but I also want FT1 now. So it's in the x direction, so let's take a look in the x direction. I would have, in the negative x direction, we have FT1, and something has to be balancing that out if the sign is going to stay stationary, and we want it to. Oh, we have an x component of FT2, and that's pointed off to the right because the wire points up and to the right. So our x component does the right part of that. The y component does the up part of that. They work together to make the large vector. So I have in the negative x direction, FT1, which is what I'm after, and in the positive x, FT2x, which I don't know off the top of my head, but I have a triangle up there that I can use to solve for it. And since we want our acceleration in the x to also be 0, the sign to stay stationary, we can then set that equal to 0 to find out what we would need. Okay, so in this, I could then find that tangent of 60 degrees, that would be our opposite, which is 20 newtons, over our adjacent, which is FT2x. Or you could use the 23.1 newtons as the hypotenuse and actually solve for it that way. Both of those are perfectly good. So I would get, doing a little bit of work on this, I would have 20 divided by tangent of 60. And I would end up with, we find that FT2x is equal to 11.5 newtons in magnitude, and it's off to the right. So now I can add FT1 over to the other side. FT2x is equal to FT1 in magnitude, and therefore FT1 must be 11.5 newtons. And there, we have now found both of the tensions. And we've also introduced how to work with forces at an angle. Here's where some of that trigonometry comes back in. Okay, I'm going to stop the recording and then start it back up in just a moment, and we will quickly go through and finish up our force list. Back in a moment. All right, so picking back up. We've got 2 more forces on my force list, and there'll be an additional one if you're not in my class for the spring force, since that is now explicitly laid out for this unit according to College Board. As of right now, we still are going to put that off, so maybe I'll change that in the future. However, we are now to one of the important ones for us to talk about, drag force, or air resistance. Now, it's technically referred to as drag force because it isn't always a resistance supplied by air. In fact, many questions on the AP exam have it just as a resistive force. Okay, let's see. So in this case, broad description of this would be a resisting force, or a resistive force, from moving through a medium, is the technical term. For us, that basically means air or water. Those are the main ones that you end up seeing, or they'll just have it that they'll say it's a resistive force and give you a function of it if you have to do calculus. Now, one thing that I'm going to bring up on this is the video that I plan on using for both my algebra-based class and my calculus-based class. So we're going to talk about some of the things that the calculus-based class would see. So if you're one of these students in the algebra-based physics, you would not necessarily need to know all of these things. In fact, for algebra-based, you won't even need to know the equations that I write down on this. You would just treat this like a normal force, for want of a better term, if we asked you to solve for it in any context. For my calculus-based class, we're going to introduce the basics on this, and then there will be additional videos, because those are going to be entire lessons unto themselves, where we explore how this will show up and how to work with this. In short, drag force requires calculus, and so that's why it's a common question on the APC mechanics exam, and it's also one for the calc-based physics specifically. A little bit of commentary on this. Drag force always points opposite of velocity. And as you have objects that change direction, At any given point, whatever your instantaneous velocity is, the drag will point the opposite direction of that. So a lot of the problems that we might look at might include things that change direction, and that makes it a pain to kind of work with them. We'll tackle those when we get to them, and they're few and far between on the AP exam. So in this case, I'm going to give you two different versions of the equation. The first one is the technically correct one, or at least a better representation of it. Drag force is equal to a constant times the velocity squared. I'm going to go ahead and mark that this is for, it's not just for high-speed objects, but for our purposes, I'm going to say that this is where you get a distinction on it. This is the actual equation for drag force for both air resistance and for water for that matter as well, at least for the introductory classes on how you would model it and do all of that. This will carry you all the way through at least graduate level, as if I recall correctly. In this case, if you've got something going through air, which is a lot of the things that we might look at, getting significant drag force requires you to be moving very quickly. So for cars, for planes, for most of the stuff moving through air, this would be the appropriate equation. Though when we get to the lessons on actually doing the calculus on it, these can be a little bit harder to work with. It's actually much easier to use the equation of Fd equals K times V. Not V squared, but V. And this is an approximation that holds pretty well when you're working with low speeds. So for instance, if V were 100 and you square it, this is an oversimplification, it would go up to 10,000, a much bigger number. But if V is about 1 and you square it, well, it just stays 1. And so that's kind of a hand-wavy mathematical way of approaching it, because if I'm going 1 meter per second, I can just switch it to centimeters, and then I'm going 100. So that's not the actual full reason of it, but this is one where this becomes a good approximation when you're dealing with low speeds for a couple of reasons. Your velocity doesn't get so large, so the squared doesn't have near as much of an effect. This one has a tendency of applying if you're looking at stuff going through water, because water ends up keeping the speeds usually pretty low unless you're dealing with something incredibly powerful. We have seen both of these on AP exams before, and they are the common ones to work with. This one is the better representation of reality. This is a good approximation for many situations, but not all. When we get to the actual video going through that, the lesson on that, we'll take that apart a little bit more. In short, the calculus is much easier to do on this, and while we want you to be able to do the calculus, we're not necessarily going to put you through the ringer on getting difficult calculus. Okay, enough about the calculus that may or may not be in your future. Let's talk about what we're actually looking at. Fd is drag force, or a resistive force. Sometimes it's just called that on the APC exam. K is a constant. Now, it's not a universal constant. I'm going to mark that this is just a constant. For many students, when they learn to work with this, they never actually learn anything beyond the fact that it's a number that stays that number. I'm going to go ahead and bring this up. Aerospace engineering is a passion of mine, and so what you've actually got in here, among other things, is going to be the constant will depend on the density of the fluid. That's one thing that shows up in here. And another big one is, I'm just going to put the word for it, aerodynamics. In other words, this constant has a couple of things that are built into it. If you go into aerospace engineering, you'll actually find that we're combining several constants together. The density of air or density of the fluid, for instance. And then we also have the drag coefficient and a couple of other things. Ooh, another one of those coefficients. I wonder what units it might have. Although that might actually have units. It's been a while since I looked at it. But in short, there are ways that this K is representing several other things that when you go in to study this more professionally, or as a more focused class beyond just an introductory, there are a couple of things that go into it. The numbers will change for different objects based on what they're moving through and the shape of those objects. So for instance, if you put your hand out the window on the highway, first off, how much force you feel definitely depends on the speed. So if you put your hand out the window while you're driving down like a neighborhood road, I hope you're going like 10 or 15 miles per hour or at maximum 25 miles per hour, you feel a little bit of breeze on your hand, but not a big force. It might push a little bit, but not much. But if you put your hand out the window on the highway, you feel it pushing a lot more. So the force depends on the speed. But one of the other things would be the aerodynamics. So if you put your hand out flat, you feel a large force. That's poor aerodynamics. It doesn't cut through the air well. But if you take that same hand and you put it like this is a much more aerodynamic orientation. You are effectively changing this constant because that constant is describing several things, which include the aerodynamics, which is a very complex statement to unpack. But so you have an idea of what this constant actually means. For many of you, you'll just go, hey, it's a constant, so I ignore it when I'm doing a derivative or integral, that sort of thing. You do you, but if you want to go into aerospace engineering or something similar, this will be important. And then finally, the speed. Or technically it's the velocity, though for the magnitudes, you really specifically would only need how fast the thing is going. We could go in and we could actually put the units on this, but I'm going to leave that for the other lesson. In fact, this is about as far as I want to talk about the drag force. It gets you more information than you possibly need at this point, and depending on what class you're in, but it does give you hopefully a well-rounded understanding of what each of these things are. I do try and make certain that when we talk about forces, and anything in physics for that matter, that we try and connect it to something real as best we can, so it's not just numbers on the page, it's something that we can think about. And that's one of the reasons why my students usually do fairly well when they get to the higher levels and on things like the AP exam, because they're thinking about what they're doing. Okay, last one, and it'll be very quick. The force of thrust. This is another one that partly it may be my background in aerospace engineering that I put this out as a separate example. But for our purposes, it's a force from a rocket or jet or propeller, or I'm just going to put fan engine. Basically stuff that would make a plane move. And we talked about this earlier where cars, the engine does make the car move forward, but it doesn't actually push on the car. Rockets, jets, and fans push on the actual vehicles, whether you have them in contact with the ground or not. Now, some of them might get a little bit more complex. Fans and jets technically interact with the air and are pushing on the air, which we usually ignore, but in this case you could just treat it as though the engine is then pushing on the object. Rockets, that's why we need to use those in space. They don't actually have to push on anything. We'll come back to how those work later when we study momentum. All right. For our purposes, this isn't something that actually shows up on the AP exam. They have had the force from a fan, and they'll usually put like F fan. But in this case for us, because we will sometimes make reference to it, I will usually use FTH for thrust because T was already taken by tension. This one, like many of the others, has no direct equation, at least for the level that we are at, because it all comes down to the design of the engine. Okay. That is our equation list. I'm going to come back in just a moment and show you an example of a place where the force of thrust has shown up commonly on the AP exam, but other than that, we're pretty much done with our force list. Unless you're doing the spring force, then look for the other video. Anyway, there we go. All right, real quick, I'm not going to get out the track and everything for it, but this is an example of something that we have seen multiple times on the AP exam, and I would say is a good representation of this idea of the force of thrust. We've got a fan here, and it's got a little power switch. Let me give better contrast. Power switch where I can turn it on to the low setting. And when I put this on its track and let go of it, the fan will push the cart and make it accelerate. We can collect data and try and find the acceleration of this object with its mass, and then do Newton's second law on it and try and get a good idea of what the force from the fan is. Then we can also set it to, here's the first setting, here's the second, and there's the third. So we have different power settings. This one's actually really nice too, because we can come in here and loosen a locking position, and we can actually spin this where, with the built-in protractor, I am now turning this to an angle of 45 degrees. So if we found our force of thrust from this, I can now change it where it's pointed 45 degrees off. This is not dissimilar to the tension question that we did, a force at an angle, and I could then try and predict what the acceleration would be, and we could use that to check if our force is actually holding constant or if it's changing. I've seen this on many AP exams, especially in the free response section, though sometimes on the multiple choice. So here's an example of where they might ask you about a force of thrust, but they probably won't call it a force of thrust. They'll just say that it's the force from a fan on a cart. And the nice thing about this is, while it will be on a track, it doesn't actually have to be on the track. I could put this just about anywhere and it would still experience that force, so long as there's air for it to interact with. Okay, I just wanted to finish up and show you that as an example of force of thrust in a way that you would likely to be seen, or a way that is likely to be seen. All right, until next time.